Okay. And also someone comes to me, says that I think it's the question A is also like kind of problematic. I will check in again and let you know when I update it. Okay. Right. And also about the course enrollment, I think like someone comes to me when like in the first or second sections of this course. When like after I check with the department, they say that for people, if you want to enroll in this class, and if you are a graduate student, meaning that if you are a master or doctoral student, you can enroll it directly online once the semesters opens. Okay. And if you are undergrad, like undergrad students, you have to wait until the semester starts. Like the first, I think it's the first 2 weeks. And then you can, I mean, within these 2 weeks, you can go online and like enroll this course. So I think that's the whole process. Okay. And if you have any questions about it, just email me again and I will check with. Okay, and finally, because we are going to finish this course by the end of August, okay? So, and hence, like this course is not going to appear on your course schedule during the semesters, which means you don't need to worry about the time conflict stuff, okay? Is that clear? Okay. Right, any questions before we start today? And I think like, okay. So today we are going to, maybe, yeah, so yeah, I think it will be a good practice to kind of refresh before every lectures. So let me quickly go through the topic we have covered so far, like at least in the lecture 2 and lecture 3. So in the lecture 2, what do we cover? We talk about the list upper bound property and the metric space, and also the because if you want to have a metric space, you have to have the distant functions as well. So we talk about there are 3 properties of distant functions. Okay, it's a non-negative and symmetric, and also it has to satisfy the triangle inequality, right? And then we talk about the convergence, Cauchy sequence, open set, closed set, limit point, and we also prove that there are 3 equivalent statements of closed set, right? So when you how to say that? When you see the questions in the final exam, it says that, okay, for example, A is a closed set. So of course you can use like this one of these 3 equivalent statement. That's okay because we have proved it. At least I ask you to prove it, okay? But you can take that as given. But I would like to see at least you write down that, okay, so A is a closed set is equivalent to the definition you want to use. Okay, so at least you put a statement like that, and that will be fine. Okay, and what else we covers? Like boundary, that will be the last part of the lecture 2. And in the lecture 3, we talk about the continuity and show that the convergence can be preserved by a continuous functions, and also the openness can be preserved as well. Okay. And we also talk about the compactness, and also shows that, okay, so in a metric space, the sequentially compact is equivalent to the compact. And we also show that how to operate the definition of compactness in Rn systems, which is Hence-Borel theorem, and also shows that the compactness can be preserved by a continuous function as well. Okay, and finally, in lecture 3, I showed that like all the discussion in the lecture 3 lead us to the extreme value theorem in the end. So you don't need to worry about like when you try to solve the maximization problem every time to worry about like whether that is it or not. So that's the purpose. Okay, so come back to today's class. Today we are going to cover the vectors and hyperplane. Yeah, so the first definition of today's class is the vector space. So vector space is a set with two operations here. Okay. The first one is additions, and the second one is scalar multiplications here. Okay, and it has to satisfy this 8 property. I just call it axiom here. Right, meaning that we don't need to verify it. But let me show you a little bit about like details here. Okay, so to put it in details, let's say that now we have, can you see the back, what I wrote here? Yeah, okay. So says that we have like two vectors there, u and v, and it looks like this one for each coordinate. Start from like the first one, second one, third one to n1 here. Okay, so if we add together, then it means we add up each coordinate one by one. Like the first coordinate becomes x1 plus y1, and the second becomes x2 plus y2, and etc. 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 So the t means that because I used to write the vectors in a way like this one. For example, like x1, x2, to x. But because in the board